Okay, this will just be a really quick video explaining dedicated to water. Now, water is an extremely important molecule, especially for the unit that we're just going to start, and that is solutions. Okay, our solutions unit deals entirely in aqueous solution. Oh crap, I'm butchering that spelling. Aqueous solutions. Okay. So, let's say we had NaCl. Sometimes when we're writing balanced chemical equations, we might see a bracket AQ. AQ, all it means is aqueous. And aqueous stands for anything dissolved in water. So for example, NaCl, sodium chloride, salt, table salt. When you see an AQ next to it, it means it's dissolved in water. Aqueous just means it's dissolved in water, and only in water, not in any other liquid, not in mercury, not in, I don't know, any. When it says aqueous, you know that it's in water for sure. And that's because water is very special, okay? Well, let's first look at the molecular structure of water. You have oxygen. Oxygen is a larger molecule compared to hydrogen. Oxygen is over here, hydrogen is over here. You can see oxygen has atomic weight of 16.0, 15.999, and hydrogen has an atomic weight of 1.00. So oxygen is by far heavier and larger. That's why in a 3D model, oxygen is going to take up more space. We all know water is H2O, so this is the oxygen, and the two hydrogens are over here. Now, what's special about water is that it's what's something called a polar molecule, okay? And, when you see polar, just think about the poles, right? North and south poles. Polar just means that electrons are more attracted to one side. So basically, in water, oxygen likes electrons a lot more. So remember when we talked about how elements in this area tend to have a +1, and elements in this area tend to have a -2, and that's because oxygen tends to hog electrons, and that's why it gets a negative charge. So now this is not an ionic molecule, so oxygen doesn't take the electrons from hydrogen, but the electrons tend to be near oxygen. If these were the electrons, they tend to be near the oxygen because the oxygen nucleus has a greater attraction to electrons than the hydrogen one. Now, the hydrogen nucleus has a weak attraction. That's why hydrogen tends to form +1 charges. An electron tends to leave hydrogen, right? Whereas oxygen tends to gain electrons. That's why it tends to have a -2 charge. So oxygen tends to hog more electrons and hydrogen tends to gain more electrons. And because of this, oxygen tends to be negative. This end of the water molecule tends to be negative. Now, it's not a full charge. It's not like O2-, right? It just tends to be a little bit more negative. It's not a full charge. Whereas the hydrogen atoms tend to be more positive, right? So you tend to have a 2- here, a plus here. Now, usually you just might write it as minus and plus, not a 2- because these are not full charges. But just know when you draw a water molecule, this side, the oxygen side tends to be negative and the hydrogen side tends to be positive because the electrons tend to be attracted to the oxygen nucleus more than the hydrogen nucleus. And because of that, the hydrogen nucleus tends to have less electrons, and because it has less electrons, it has less negative charge, therefore more positive charge. And vice versa for the oxygen atom, because it tends to hog electrons. The nucleus of the oxygen atom tends to hog electrons. It tends to be more negative, and because it tends to be more negative, it tends to have more electrons. It tends to be more negative. Yep. Okay. And this polarity of this molecule makes it so that it can dissolve a lot of things, right? And I'll show you why in the next slide. Okay, let's forget about this terminology and go straight to this picture. So you have NaCl from the last example and water. And here's our legend. The sodium atom is a positive because we know Na+. Oh, my bad. No. Yeah, here, right? Sodium is in the first column, so it tends to have a +1 charge. Chlorine tends to be in the halogens, so it tends to have a -1. Remember, -3, +2, etc., etc. So sodium is +1, and chlorine, in this case, a chloride ion because it's charged. Remember, Chloride means it's an ion, it's charged, and chlorine just means it's neutral. So in this case, you have sodium chloride, and we've all seen table salt on the table. That's its solid form. But we also know that salt dissolves in sugar, right? In the ocean, salt is dissolved in the ocean, and that's aqueous. So NaCl in the aqueous would be something like what you would find in the ocean, whereas NaCl solid, the solid symbol, would be something you find, if you buy from the supermarket. It's in its solid form. Okay. So what if we put some NaCl into water? We know it dissolves. And why does it dissolve? It's because water is polar. So you see here, the oxygen atom is negative and the hydrogen atom tends to be positive. Okay, positive, negative. And the symbol just means it's negative. It just designates that it's a polar molecule. Okay, so anyways, and you see here that the negative end of the negative end of the water molecule, so the oxygen parts, tends to be attracted to the positive sodium ion, which makes sense. Sodium is positive. It has a +1 charge because it's in this column. It tends to have a +1 charge, so it tends to be attracted to negative things. Now it is attracted to chloride when it's outside of the water, but when it enters the water, what actually happens is the negative parts of the water molecule, so the oxygen side, becomes attracted with the positive sodium ion. And what happens is the water molecule surrounds the sodium ion, and so it splits the sodium ion from its chloride ion. And now for the chloride ion, the opposite happens. The positive hydrogen ends of the water molecule start being attracted to the negative chloride ion. And what happens is now the negative chloride ion is surrounded by the positive hydrogen atoms of the water molecule, and the positive sodium ion is surrounded by the negative oxygen atoms of the water molecule. And what happens is water just basically separates the sodium and chloride ions. And because of that that you see sodium chloride dissolving. It's because when, for example, sodium chloride, and it doesn't have to be sodium chloride, it could be potassium chloride, it could be, calcium nitrate, right? Usually polar substances, so salts, let's call these salts, because these are also called salts. This is, the common name is table salt, right? So, but there can be many different kinds of salts. But basically, if something dissolves in water, this is how it would dissolve. The compound, in this case NaCl, splits into positive and negative ions, and these ions are surrounded by water molecules. The negative ion, in this case chlorine, is surrounded by the positive hydrogen atoms, and the positive ion is surrounded by the negative oxygen atoms. Okay, now let's go with some terminology. We'll be using solvent, solute, and solution throughout this course, and it's just something you should know. Solvent is what's able to dissolve other substances. So in this case, water. And I've already said water is the universal solvent. Universal solvent. Okay? So basically, water is a universal solvent. So water dissolves the most solutes. And what solute? Solute is a thing that's being dissolved. So NaCl would be the solute. Okay, so in this case, the solute is NaCl, and solvent is H2O, or water. Okay, the more common name is water. Okay, and usually you can tell, a good rule of thumb is solute is what's less of. Okay, so if there's less, there's usually less sodium. It's very rare that water can dissolve, something more than it. Okay, if you imagine you had 100 grams of water and then 100 grams of salt. I don't think, correct me if I'm wrong, but I don't believe NaCl can dissolve. 100 grams of water can dissolve in 100 grams of sodium chloride. And the reason for that is because, just think about it from a geometry perspective. One positive ion needs what? 1, 2, 3, possibly more water molecules around it. So, you're going to need, if you have one sodium ion for every, one water molecule, that's not going to work out. Now, of course, this deals with masses and not moles, but you get the point. And either way, sodium chloride weighs more than water, so you wouldn't be able to dissolve this much sodium chloride anyways. Okay, solution. Solution is just a solute plus a solvent. So when you dissolve, when you dissolve NaCl, let's say these are the dissolved ions. This Cl, this is Na, Cl, Na, yada yada yada. Then this whole thing would be the solution. Okay. So, for example, this would be a solution. If this was dissolved. After this dissolved, this would be the solution. If NaCl is just in a solid form, it would be called a precipitate. It just means solid in liquid, solid in water. Okay, and all aqueous solutions are solutions. It's an aqueous solution, so it just means something dissolved in water. So, for example, if you saw KCl aqueous, it means potassium chloride is dissolved in water. If you saw I don't know, calcium nitrate aqueous, this means it's in water and it's dissolved. Okay, so it's not like the calcium is still bonded to the nitrate. Okay, what's actually happened is that when you see calcium nitrate in solution, you have calcium ions here, and separate from it is nitrate ions. Okay, or for example, potassium chloride. If you see potassium chloride with an aqueous symbol, all it means is that you have potassium ions here, chlorine ions here, chloride ions, potassium, and they're not bonded together. There's water molecules surrounding these potassium ions. Okay. This would be hydrogen. Yep. Okay. Potassium chloride. And yeah, that is just an introduction to water.